The purpose of our final lesson is to take a look at what we've been learning about operations in algebraic thinking and to apply it to curriculum, particularly thinking about the strengths and weaknesses of our curriculum and where it might need to be supplemented. To do that, we need to think about what the Common Core authors think we should be looking for, and the standards of mathematical practice are a really important one. In the past, a number of textbooks have looked at mathematical practice standards as an occasional event rather than as integral to all learning, and so you might find that each chapter has a page at the back that's all about learning a new problem-solving technique, for example. But in the Common Core state standards, the authors have been very clear that the mathematical practice standards are the means, the avenue by which the content standards are developed, so that they should be fully integrated. There's also learning progressions, many of which started in previous grade levels, that we need to be very cognizant of and ensure that in our grade level that the aspect of Common Core state standards in that progression for our grade level is being fully developed using the foundation that came before and preparing students with a foundation for the future. And because we have clear expectations for where they should be at the end of the second grade year, we need to recognize that practice alone will not get all of our learners there. So we need developmental learning sequences that build on the strengths and the prior knowledge they already have to gradually grow their expertise and sophistication by the end of the year. The Common Core authors use all of these terms quite regularly. Focus refers to what you spend your time emphasizing in the second grade curriculum. And that includes the standards, but the standards should go deep and they should be related to other important concepts. For example, operations in algebraic thinking relate very well to number and base 10 standards as well. Coherence refers to these progressions that are built across grade levels and how we need to be very clear that we are not an island. The students come to us with the foundation that was built on the grade level before. We are adding to an existing knowledge set, and we need to be very cognizant of that and ensure that what we're doing builds a careful, coherent sequence of knowledge. And finally, the authors talk about rigor. And rigor, they say, is three-pronged. It includes conceptual understanding and procedural skill, fluency, and applications. That you cannot have a rigorous curriculum without all three elements being developed. The mathematical practice standards then are merged throughout all of this as being the how that we learn these content standards. The publisher's criteria, and I'm going to include a link to these if you in the teaching resources. If you are on a curriculum committee, if your school's looking at purchasing a curriculum that will be more in line with the Common Core, you really need to examine the publisher's criteria. They help you determine what you should be looking for, and they also help publishers to try to craft products that will be more helpful to you as well. In the publisher's criteria, the authors are very clear that the student's conceptual understanding of the key mathematical concepts that are developed in the standards needs to be the primary focus, that there needs to be an attention not just to conceptual but also to procedural and to applications, but that their experience with applications shouldn't detract from the concept development but actually enhance it. And of course, the content standards and practice standards are fully connected. So let's take a look at this domain that we've been studying and consider what those primary learning progressions are. And the first three bullets refer to learning progressions that started in previous grade levels. The first two are the progression represent and solve problems. And the thing that's differed at various grade levels is what kind of problems are required for mastery and what number set. And so here you now see that at second grade, this represent and solve addition and subtraction problems progression is to reach fruition by the end of this year, where students are able to represent and solve problems of all of the different types. We talked about the types of problems in the first two lessons in this PD module, and also with number sets up to 100. We've spent most of our time talking about computation within 20. In the number and base 10 PD module, we will extend those strategies to strategies within 100. And so we also talked about two-step, and the two-step problems are fairly new. And we talked about what levels of two-step problems are going to need to be developed as well. So that's another thing that's critical. And when you look at your curriculum, you need to take a look at whether all of those problem types, as well as the two-step problem types that are required, are evident in your curriculum. Fluency. We talked about mental strategies for fluently adding and subtracting within 20, as well as the sums of the two single-digit numbers. And we talked about the importance of using conceptual understanding to inform those strategies. Well, actually, reflexively, they inform one another. Building the strategies helps build the conceptual understanding, and the conceptual understanding helps to build the strategies. And finally, a brand new progression for second grade, making sense of multiplication as an operation. We're going to specifically focus on some of the content or the practice standards that really lend themselves to these topics, and I could have gone into detail on more, but the lesson would have got too long. So I'm taking 3 of the practice standards and particularly looking at how that can be applied so that the content you're learning reflects that. To do that, we're going to take a look at Mathematical Standard of Practice 1, Make Sense and Persevere in Solving Problems. Of course, that's integrally involved in the first couple of bullet points on that list we just looked at. What is a problem, though? If we're going to talk about solving problems, we need to know how the Common Core authors perceive problems, and it turns out that they might be perceiving them differently than you do. In the past, we've thought of problems as being synonymous with word problems, but not all word problems are problems. In order for something to be a problem, as stated here by the Common Core writing team, it must be a situation where the students don't know what to do. If the students already know what you want them to do, then it's an exercise, not a problem. So I remember books from when I was in high school, the way the math texts were set up at that level. On the left-hand page, it said, here's our new skill, this is how you do it, this is how you solve a problem step by step. And then over on the page on the right were a set of problems, and you were supposed to apply that exact procedure to the problems on that page. By this definition, those were not problems, even though they looked like word problems. They were exercises. So we need to examine our curriculum and say, when I look at these word problems, do the students have to make decisions? Do they have to deeply understand what's going on? Do they need to model relationships and think about how they'll play out into equations? Do they have to make decisions about what process or procedure or heuristic to apply? Or do they already know because the way the textbook laid it out, they're just supposed to do this? Think about those as you consider what to call a problem and what isn't a problem in your curriculum. The Common Core authors also talk about the value of problems because they are important teaching tools that actually allow students to build their mathematical understanding. And that's also fundamentally different than the way word problems have been perceived in the past. Oftentimes we just wanted students to get an answer. And when that was our goal, we gave them help. Oh, that's a subtraction problem because we thought the goal was to get the answer, so they're getting stuck on whether it's add or subtract, so I'll give that to them. In effect, we actually bypassed the real learning. The real learning was to make sense of situations where this operation is evident, and to help them get to the point where they can see what makes subtraction that would cause this problem to be subtraction. So that is the math that's being built there. And I wouldn't want to bypass it. I would see that as now more important than just getting to the correct answer. Let's take our time with that, even if we don't get to an answer. So that shifts our focus about how we're using problems as well. Problems are very versatile teaching tools. They can be used to build new knowledge, bring out misconceptions, build skill or fluency, and also to get students to engage in the mathematical standards of practice. And not just the first one. You'll see that it shows up in others as well. The authors, although they value problem solving very much, do not think that this is a situation where more is better. They would prefer fewer problems in a lesson with more goody out of them. So more time spent talking about, thinking about, representing, comparing strategies, trying to pull out the math in the problem rather than being able to solve a lot of problems. So they'd rather see 1 or 2 problems that are complex enough that they really build perseverance and math content rather than 10 word problems that are fairly simple and which focus mainly on practicing computation. The problem solving, we often think of that as a procedural skill perhaps, but in reality it includes all three of the components that make up rigor. And I'm not going to go through all of that now in the interest of time, but I encourage you to take a look in your notes of the different ways in which problem solving can build conceptual, procedural, and application skills in the curriculum. So when you take a look at your curriculum, here's a couple of things to really look for as you skim through the pages looking at the word problems. Is there variety so that the students have to make decisions? If there's enough variety of word, when you see clusters of word problems, do the students see that these problems are not all the same type, that they're going to have to make decisions, that they will not start in reading it knowing already what it is? And is there an opportunity for enough richness there to actually build some mathematics? If all of the word problems are essentially result unknown, that's the easiest problem type. Even if they have big numbers, that's probably just building their computation skills rather than building their math. You need to have some more difficult problems and problems that are two-step, for example, to really help them make sense and perceive relationships. You can also have problems that aren't the classic word problem example, and I'll give you an example of those here in a couple of minutes. When you do look at the word problems, however, you should see some start unknown problems, because quite a few actually, because students are to master that in second grade, and some compare problems where the terms more and fewer are used in counterintuitive ways. And then also to look at whether there's some good math that can be built by working on these problems. Here's another curriculum checklist. From these ideas come from putting the practices into action. Are the students given problems that actually require them to persevere? A steady diet of fairly easy problem structures do not build perseverance, no matter how many of them you give the students will merely come to think that if they don't know what to do right away, they should give up and ask for help. They need to actually have enough variety and complexity embedded in their assignments that they recognize that perseverance is desired. Are there problem-solving behaviors and heuristics being fostered as opposed to shallow tricks like keywords, which don't build the math at all? Are the students given opportunities to talk about and write about their problem solving? This may not be evident in the written curriculum, but is certainly something that you can do something with in terms of the implemented curriculum. Does it appear that there are tons of fairly easy problems or 1 to 2 rich problems that students can really sink their teeth into and develop their strategies? And are there some good embedded mathematical ideas so that a strategy share could be a rich dialogue? Now, this is an example of a heuristic. A lot of texts don't have this aspect fully developed, and so I really love this tool, this process skills for problem solving, and it's in the references section if you're interested. But this is an example of draw a diagram from that resource, and here you'll see that it begins with a fully worked model. And when I do this on the smartboard, they only look at part of it at a time, so we study each part. When I reveal the diagram, we've already of course discussed the question, and we talk about why does this model make sense? Is it helpful? Why take the time to do this? Does it give us insight? How is it helpful? So we work our way through that. The students then have practice problems, and this is an important thing to recognize. The practice problems are difficult. If you don't use the heuristic, they're much harder. And so this helps the students see real advantages to using the heuristic. If I gave a word problem that didn't even require that model, it would just seem to the child like it was more work than if I just did it this way. So they won't really adopt that heuristic. But if you give them some problems which really require that, then it's a tool that can be added to their repertoire. And when they get stuck and you're trying to foster perseverance, you can actually refer back to your list of heuristics that you have on the board. You can call it something more user-friendly and say, which of these tools that we've learned about would be especially helpful for this kind of problem? What could you try as a way to help them build perseverance? This is another example of heuristic from Scott Forsman, Addison Wesley, and it is a useful tool. They're actually looking at combinations of tens that can get a particular total. Now, if you do this and you think that the goal is to get the correct answer in each field of the matrix, then it won't be all that great of a learning experience. But if they really look for patterns and talk about why that pattern exists, this could be a really great learning tool. Unfortunately, in this curriculum, there aren't any real practice questions after this that require them to do it, except ones that fit the exact same model. So based on that, the child could think that make an organized list was a highly idiosyncratic tool that was only rarely useful if you had a problem that fit this problem type. So I think it would be useful to have some more practice problems. If I were using this text, I would be looking for other problems where make an organized list would also be helpful so that I could follow it up with some of those examples. Mathematical standard of practice 4 is model with mathematics, and problem solving is just rife with opportunities for building models, and those models can be concrete. They can be visual representations such as tape diagrams and number bonds that are talked about in Common Core, math racks, arrays talked about in the Common Core, as well as the more abstract equations. But these are not things that just merely showing or prompting students will, not merely prompting them, will result in the kind of meaningful use of models that we want students to develop. We want them to make connections between these. We want them to use them as tools for mathematical understanding, and that's going to require some development and instruction. So again, the process skills for mathematics that I showed you earlier, here's an example of how they build students' model skills with two-step problems using the tape diagram. And again, we have a fully worked example followed by a lot of practice problems where building the tape model is really helpful. And finishing with this one, it has an asterisk by it, so it is one of the hard problems that might be for your students who particularly like a challenge. But when you look at this problem, you'll see that it is difficult for second grade, and that the tape diagram can be a really powerful tool for making sense of all of the aspects of this problem that are present there. I show this slide primarily so that you can see that multiplication can also be developed using the tape diagram and the number bond. I also wanted to show you that in the practice problems, the first problem draws the model and asks you to use that model to help think about what kind of equation would make sense. And then the very next problem, the model goes away and you have to think about it yourself. So this is a true scaffold, a fully worked example that you can study together and think about and make sense. Then a scaffold where you now have the model, but you have to do the sense making. It's not laid out for you, followed by an opportunity where you're on your own. You got to fly. So the training wheels are taken off. That's what a true scaffold is. It's temporary, then the training wheels are taken off and you're expected to be able to do something on your own. And mathematical standard of practice 2, reason abstractly and quantitatively, fits in very well to this domain because the work that we do with mental math and strategy development is all tied to the properties of operations and the way our number system works and how we can decompose and recompose number. So there's a great deal that students can develop in terms of reasoning abstractly and quantitatively by developing strategies, articulating their strategies, justifying their strategies. These images from text show how certain visual representations can foster strategies, but can also lead to this capacity to reason abstractly and quantitatively. For example, in the top left-hand corner, the particular array that you see can be used as a tool to justify why 4 times 8 and 8 times 4 have the same product. The examples on the left of your screen show how students can use what they know about the properties of addition, and this is actually the associative property of addition, even if they don't know it by name, that allows them to decompose and recompose and add in any order, and how they can use that to their advantage in a mental math strategy. So here are the curriculum examples, and the top one under curriculum examples by Li Fang Lang is process skills and problem solving. It's available from singaporemath.com, although it is